Okay, we're starting. Alright, so last time, let's just do a small recap. We'll talk about some new facts, then we will do the examples and talk about even more facts. So last time we were talking about homogeneous second order linear differential equations with constant coefficients. What do these guys look like?
Y double prime plus
Plus what?
Oh, where A is a constant.
Constant coefficients.
A,
So we'll do them more generally later.
AY prime.
So you can do AY double prime plus BY prime plus CY equals 0. You can also just assume this is 1, do something like Y prime plus AY prime plus BY equals 0. Either way. So now, how did we actually solve this? What did we assume the solution to be? Y equals e to the RT, because we want something that is very similar to its own derivative. So that was the general form. I'm actually going through the first few quiz problems. So that was the general form you should have written down. This is the assumed solution, and then 3 cases ensue. What is the first case?
Real distinct.
So case 1 is real. You don't have to mention real, but just mention distinct roots, I guess. Real distinct roots. Right, so you have 2 roots because you end up. Well, we're missing something. This actually leads to, if I were to assume this is y, plug into that, I'm going to get a quadratic equation. This guy is called a characteristic equation. We'll mention it next time. And so you get a quadratic, and once you try to solve that quadratic, you have 3 cases. One possibility is that you have 2 distinct roots of R1 and R2, with R1 not equal to R2. So that was one case, you have distinct roots. And what does the solution look like in this case?
C1 e to R1 plus C2 e to R2.
The second case.
Repeated roots.
You can have repeated roots, so that's how we describe it in words. And what do those guys look like?
Same as the other one, but it's R1 plus
Plus C2T e to the R1 T. I'm hoping we have some time today to justify that. Why the T? Case 3.
Complex roots.
Complex roots. And in this case, what does the solution look like? C1 e to the AT cosine BT. Or, yeah, the book uses alpha and beta. Let's stay away from the Greek letters. You don't want to. Anyway. And C2 sine BT.
I have a question.
Yes.
I just want to know, how do you find the constants in the file? Like with y?
As in the C1 and C2?
You need initial conditions.
Well, you need initial conditions. So for some of the examples that I gave you on the board last time, it requires that. So since this is all we need to know to do those examples, let's just quickly run through those examples.
Another question. Wouldn't there be an I in front of sine B? I know it's like
I is a constant, so we put it inside the C2. So now, technically we already know how much to solve, even though we probably don't know what we're doing while we're doing this. Between this class and the next class, which by the way is next Wednesday, remember there's no school Tuesday and Wednesday.
Wait, what?
Yeah. Yes.
This whole Monday?
I sent an email about it. Just read your emails. So there are no classes Tuesday or Wednesday, and then the following Monday is like Columbus Day or something. So The next time I see you is next week Wednesday. And hopefully then what I want to talk about next week Wednesday is actually the existence and uniqueness theorem. I want to talk a little bit about those guys and how they actually are going to flesh out. By the way, to that end, in the email I sent you a couple of videos of me teaching something in 392 that will be, it's not going to tell you anything, it's not going to tell you nearly enough, but it will make you feel like you're not completely lost when I'm writing things on the board. Oh, that looks familiar, right? I just want you to have that feeling, because technically we don't have anywhere near the linear algebra needed to prove the existence and uniqueness theorem, and that's actually not your fault. We just don't teach as much linear algebra needed to do something like that theorem, even in the math major version of linear algebra. So I'm going to be very hand-wavy about it, but hopefully by you watching that and you reading up on Cramer's rule and systems of equations, you'll get to kind of see why things work out the way they do. I'll probably also mention the existence and uniqueness theorems today, but I probably won't discuss why they're true today. I'll say that for Wednesday. Because we won't have time to do what I want to do and do that. That's going to take some slow burning. Plus, you guys should watch those videos that I mentioned, because you should know about our eigenvalues and eigenvectors and what the solution of a system of differential equations would look like, et cetera, et cetera. Just have some idea. That will make our Wednesday discussion a lot more productive, even though it's not going to be 100% productive. Anyway, let's actually jump into examples. So in the bonus for the quiz, I gave you several more examples that are going to be attacked similar to this. I'll write the answers to those, so let's attack these ones here. The first one was y double prime minus 4y prime plus 3y equals 0. So this is a second order linear differential equation with constant coefficients. So immediately when you see that, you're going to assume y equals e to the rt, and you're going to plug that in to the function, and you are going to get a characteristic equation. Now, you don't need to write that down every time, by the way. I'll write it down just one time so you can see what actually happened again, just to remind you. If you assume y equals e to the rt, then that means your y prime is equal to r e to the rt, your y double prime is equal to r squared e to the rt. You plug those all in here, you would get r squared e to the rt minus 4r e to the rt plus 3 e to the rt equals 0. You can divide both sides by the exponential because it's not going to be 0, and you will obtain the characteristic equation, which is going to be r squared minus 4r plus 3 equals 0. This is the characteristic equation.
I have a question.
Yes?
If you have a question like A, you know, y prime is positive, y double prime is positive, y prime is negative, and y is positive. Can we assume that it's sinusoidal, like cosine?
No. Yeah, so the cosine or sine only comes up in complex roots, which means if you get a quadratic where there are complex roots, that's where your sines and cosines are going to come from, which you probably won't see it in the beginning.
I have a question. If we just assume that the answer is e to the rt, why can't you just assume the answer is sine rt? Because like, why do we have to stick with that? Because sine also has like, you know.
Because the e is far more general. I mean, if we started with that guy, what do you think these cases would actually look like?
More complicated.
Like way more complicated. If we made that the base case,
Yeah.
right? This is the elementary, like the base case. And I were to work backwards and look at this simple case.
More work.
It's kind of like when you're inventing complex numbers. Why is I the square root of minus 1? Why isn't it the square root of minus 17? Because the numbers are going to be ugly. There is no other reason, right? Leave e to the rt as the base case. It's the easiest, most simplest, most straightforward function. I didn't want sines and cosines necessarily. I was forced into that position by Euler's equation. So the exponential is the most general function I know that would behave something like this. So that's where I start. Plugging that in, I obtain this. And again, the other part to that question is going to be the existence and uniqueness there is going to say it doesn't matter. We'll get there. Ultimately, you get here. Now, in practice, you don't need to write this down. You can see this and immediately write that. The y double prime is going to turn into an r squared. The y prime turns into an r. We just ignore the y, create that quadratic. It's going to be called the characteristic equation. Now you want to solve this for r. How do we solve this?
R.
Does it factor?
R is 3 and 1.
-1,
3.
-1, -3.
Right, that actually works. So you get r equals 1 or r equals 3. In other words, your general solution, which is the best we can do here because we don't have any initial conditions, is going to be c1 e to the 1t plus c2 e to the 3t. And that's going to be your general solution. Yes?
Does anyone know what order you write it in?
No. Let's go on to the second example. 2y double prime plus 3y prime minus 2y equals 0. The characteristic equation is going to be 2r squared plus 3r minus 2 equals 0. Does that one factor?
Yeah. 2R minus 1 and R plus 2.
2r minus 1.
And R plus 2.
That's 4r minus 1r given plus 3r, that's minus 2. That actually works. So here I get r equals 1/2, or r equals minus 2. So your y is equal to c1e to the t over 2 plus c2e to the minus 2t. That's your solution right there. These guys are not so bad, right? Don't worry, we'll get something more challenging later. I know you guys are very overwhelmed. It's like, I want the hard problems, but this is too easy. Don't worry, don't worry. It's just the basics, we'll get there. The third example, C. Oh, is it? This one gave us initial conditions, so we're going to answer your question about how do you find the C's. Here we're told that y of 0 is minus 1, while y prime of 0 is minus 7. Now we need two initial conditions because we have two unknowns that we need to solve for. So we can't have two unknowns and only one equation. So that's kind of where these initial conditions come from. And
It's the same as the other one, right? Or
yeah, we already solved for the other one.
Yeah,
So what I would say is y is equal to c1 e to the t plus c2 e to the 3t. Previously solved. So I put the same question again because I figured someone was going to ask, how do you find the C's? And I'm like, okay, remember, let's pick up here. Then, what's going to happen is y of 0, we need to know what y prime is because we're going to need to plug that in. So what I would do at this point is find the derivative, which is going to be c1 e to the t plus 3c2 e to the 3t. Then y of 0 equals minus 1 means that the output y is minus 1 when the t value is 0 in this function. That means c1 plus c2. And y prime of 0 is equal to minus 7, but that is equal to when I put in 0 for t here. So c1 plus 3c2. What you have now is a system of equations. Now you're starting to see where the linear algebra is coming in. And you can imagine for like nth order differential equations, we have like n by n systems and all that stuff going on. And that's how we're going to use it. We're going to figure out how to solve these guys using linear algebra. And that's going to give us the existence and uniqueness theorem with some work behind it. Anyway, so here, this is equation 1, that's equation 2. I can do something like take equation 2 minus equation 1.
Multiply it by 3 maybe?
No, you would be option
Well, I could also do that.
The easiest way is to multiply equation 1 by 3 and then subtract
You
it.
can just solve for C1 first.
That's the easiest way.
Okay, so you're telling me multiplying something by 3 and subtracting is easier than just subtracting?
Yeah, oh yeah, I guess you can.
I literally can subtract without multiplying.
I have now strong through my
There's a whole operation. Okay. I subtract 2 minus 1. We have minus 6.
Yeah.
I set up a matrix to minus 3. It's like, oh, set up the matrix and do Gaussian. Yeah. So your C2 equals minus 3. Now all I have to do is plug it in here. So minus 1 equals C1 minus 3. So my C1 is going to be equal to 2. So this means that y is equal to C1 2e to the t and C2 minus 3e to 3t.
Yeah, it's the same.
By the way, this is called the particular solution. I think I introduced that phraseology before, but just in case I didn't. So that's how you go through and find the arbitrary constants here. You would need to be given initial conditions, apply those initial conditions. You will ultimately get a system of equations that you need to solve for these guys. Do it the easiest way you can, or the hardest way you can, as might be preferred. But ultimately, you want to get to the answer, and once you find the C's, you go back to the general solution and plug them in. And so this is the particular function that solves that differential equation, and it passes through the point 0, minus 1, and its derivative passes through the point 0, minus 7.
Is it wrong to look at this as, like, analytically instead of doing it?
What do you mean?
Because it's not too crazy to think of a function that's second derivative plus its first non-derivative thing equals 0.
Okay, what is the function?
It's trigonometric. It's got to be the second derivative of sine, which will be negative sine, plus that equals 0.
Okay. So that's your answer? Why
Well,
else?
then you have to use the other thing.
What else?
I think I just solved that and was like happy that it worked.
But that was your answer? Y equals sine?
No.
Because you're missing something.
Does R equal
Which is why we do it this way, so we don't miss anything.
I got it. Oh wait. I have it here. I did it.
Okay, so r squared plus 1, this means of course r squared is equal to minus 1, or r is plus or minus I. So this means we look at this as 0 plus or minus 1i, and we plug into the formula that I erased. But ultimately we're going to get all the answers. So it is going to be, now let me just write it out so you can see where this is coming from. Y is going to be C1 e to the AT, which of course is just going to be 1, it's going to disappear, times cosine of 1t plus C2 e to the AT, again that's going to be 1, times sine of 1t.
Yes. Why is it supposed to?
And so ultimately your y is just a constant times cosine plus a constant times sine. And that's how the signs come in. You don't have to force them, they're going to pop up when they need to. So that's the general solution there. 2y plus y equals 0. Okay. This one characteristic equation is going to be r squared minus 2r plus 1. What is this?
R minus 1 squared.
It's r minus 1 all squared, which means I get r1 and r2 are both 1. This is a repeated root. Now, this means that my solution is going to look like c1 e to the 1t plus c2t e to the 1t.
Are we going to specify the second piece there?
Good question.
Let's put a star here.
Why?
Because that why. Right, I'm going to explain why. Why does it have to look like that? So when I'm going to write a star, and you're going to know I'm starting to explain this. I didn't explain it last time. I just told you guys that that's the answer. The one with sines and cosines, you guys can see where that comes from. Also, the distinct roots, you guys would see where that comes from. But why is it that when you get one answer, you just multiply by a t? I will explain. The easiest way to do that is via a process called reduction of order. Now, I will probably talk about that. I'm so excited. There's so many things to talk about. I don't know what to do first. I could maybe talk about this. No, I should talk about that first. No, I should talk about that first. That's what's going on in my head. There's so many. Okay. So, okay. Y double prime plus 4y prime plus 5y equals 0. And we again have initial conditions here. So you see that, you immediately jump into the characteristic equation. Can we solve this? What? Can you think of two numbers that when you multiply you get 5 and you add them and you get 4? No. No. So probably we're going to minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That's minus 4 plus or minus, this is going to be 16 minus 20, it's the radical of minus 4 all over 2.
-2 plus or minus.
So that's minus 4 plus or minus 2i all over 2. So that's minus 2 plus or minus I. What does that mean for our solution?
E to the minus 2t.
Yeah.
What?
A or C1
C1?
e to the negative 2t
Cosine
of t.
b.
C2.
Should we just be factoring out that? Yeah. Should we just be factoring out the e to the 18?
You could. Oh, we need to find that.
Yeah, just so many more like chances to make a mistake.
I can do that. That's going to be fun. So, in other words, now, so my y is equal to e to the minus 2t times c1 cosine of t plus c2 sine of t. Happy now? Yes. Okay. All right, so now we need to plug in the initial conditions, so we need to know what the derivative looks like. How to find derivatives. This is
I got
take it way back.
negative 2c1 e to the negative 2t. Plus
e to the negative 2t times negative c1 sine t plus c2.
So that's our derivative. Now, let's actually figure out what this guy is. So this is going to be factor out of e to the minus 2t. So I would have minus 2 c1 cosine t minus 2 c2 sine t minus c1 sine t plus c2 cosine t. In other words, I would have e to the minus 2t times, we can combine the signs, I guess. So that's going to be minus 2, minus c1, minus 2c2 times sine, plus c2 minus 2c1 times cosine.
No, so you can just like cancel it out. Sine 0, 0.
So that's just C2 minus 2, 0.
Right, so now applying the initial conditions, c of 0, y of 0 equals 1.
C2 minus 2C1.
So that means in this guy, I'm going to plug in t equals 0. Now, if I plug in t equals 0, the sign of t is going to disappear, right? So I'm literally just going to have c1 here.
Yep.
So nothing to do, that's c1. If I plug in y prime of 0, I'm plugging in 0 here. Now again, the sign is going to be 0, so I can ignore that part. This is going to go to 1. So all I'm going to be left with is 0 is equal to c2 minus 2c1. But I know that my c1 is 1. So this means that 0 is equal to c2 minus 2. So this means that your c2 is equal to 2. This means that our function is going to be c1, which is 1, plus c2, which is 2, and that is our particular solution. It solves that differential equation, and it is a function that passes through the point 0, 1, and if I take the derivative, that function is going to pass through the origin. So that's very computational. Let's make some discussions. Okay, so first of all, don't understand anything about. Let me talk about direction. So this is a technique that does the following. So it's a general technique. Basically, it comes up when you have some solutions, but you know there are more, and so you want to figure out what are those other guys. But the method that you found the first solution doesn't really kind of pan out to find those other guys, similar to what we did with the repeated root. So the idea is, and I haven't justified this yet, but I will, if you have a second order linear differential equation, you expect to have two solutions. So if you have one root, and there's just a 1 of the e to the t's, you're like, I'm missing somebody. Who's the other guy? But then you're like, there is no other guy that I can get from the characteristic equation. How am I going to find the second guy? Right? We know there's a second guy. I'm going to tell you how we know later. So reduction of order is actually a technique to find the second guy. So suppose, and it kind of works more generally than second order. So suppose we have linear ODE, and we have a solution y1 to this ODE. like any other technique, it'll have times when it won't work. But it's something that's worth a shot if you find yourself in that position. Oh, I did something and I only found this many solutions. I know there should be more. Where do I go from here? Either you apply a whole other technique to try to find some other guys, or you do this kind of process. Sometimes the second solution second or more solutions will be given by taking, say, another solution would be assumed to be some function times the original solution that you already have. So why would that work? Well, you've already found one function that does what you want it to do, and you probably don't want to look too far for some other function. So sometimes you just guess, maybe it's just some function times the original guy, right? So if I'm solving a second order differential equation and I get e to the t is one of the solutions, probably the next solution isn't very far off from e to the t. Maybe it's just something times e to the t, right? Because that way I can still get the exponential behavior, and I still kind of have these like terms idea going on. So we pretend that there's a function, the second solution can be determined by finding some function times the first solution, and then reduction of order is the process by which we go and try to find the v of t. Now this works more generally, but it's pretty magical on the second order linear differential equations with constant coefficients that have a repeated root. So here's what's going to happen. So just to show you that this will work no matter what, I'm going to write down a general form that is going to give us a repeated root, and I'm going to show you what the second solution needs to be for that form. But again, this is a wider technique. It applies to other things as well. Now, suppose we have a y double prime plus b y prime plus c y equals 0 with a characteristic equation that yields a repeated root. Oh, I'm going to cue. Now I'm explaining the why. Why was that the answer? Okay, so say R equals R1 is the repeated root. This means that the characteristic equation had to reduce to what? Well, R minus R1 all squared, right? That's how we're going to get the repeated root. It had to come from something like that. Which means R squared minus 2R1R plus R1 squared equals 0. Now this is after we reduce and we divide out all the constants, make the coefficient of y double prime to be 1. This is ultimately what the characteristic is going to look like. So we may assume the ODE looks like the following. It's going to look like this. It's going to look like y double prime minus 2R1y prime plus R1 squared y equals 0. This is going to be the general form of a guy that has a repeated root. Because once I find the characteristic of that guy, it will ultimately reduce to this guy, which only gives me one answer for the quadratic. Now, this R1 could be a complex number. It doesn't matter for our exercise. You could have, now, although when it comes to complex numbers, they come in pairs. We'll talk about that some other time. So now, if I had that differential equation, what's going to happen? Now, this has a solution. Y1 is e to the R1t, right? That's, I forced it to have that solution, right? If I was given something in this form, it's going to reduce to this in the characteristic equation. It's going to give me one root, so I know y1 is this. So now what I'm going to do is do what I told you. Let's assume that the second solution is not very far off from the first one. It's going to be some function times the first one. In other words, it's going to be some function v times e to the r1. Now, under that assumption, what must happen? Well, if I assume that this guy solves the differential equation, it means that if I plug this in to that, it should work out. So let's figure out how to plug that in. Our y2 prime would be, I have to differentiate this. Now v is a function of t, so we need the product rule here. V prime e to the r1t plus v times r1 e to the r1t is going to be the first. So this is going to be e to the r1t times v prime plus r1v. The second derivative is going to look like, again, I have to do the product rule here. So it's going to be r1 e to the r1t times this guy, plus leave the e to the r1t times the derivative of this guy. It's going to be v double prime plus r1v prime. I can again factor out the e to the r1t here, and on the inside I would have, well, v double prime. I'm going to have, here's going to be an r1 v prime e to the r1t, and so I'm going to have two of those. Then I would have just this guy left over. So that's going to be plus the r1 squared times v.
What about the R1 in front of the E to the R1T?
What?
In the second line, the very first thing,
First R1,
the first R1 right after the equal sign.
second one,
Second equation.
To your left.
First variable.
To your left, right there.
Yeah.
R1.
Yes.
Yeah.
What about it? Where?
Where'd it go?
Where, I don't think it's in the one below it.
It is.
Yes, if I multiply this out, I get r1 v prime times the e to the rt. And then if I multiply this out, I get this one gives me the r1 v prime e to the rt. And so I have two of those. And I factor out e to the rt. Then I have the v double prime times e to the rt, put it here, factor out e to the rt. Here, if I multiply this times that, I would have the r1 squared v e to the rt. So I have r1 squared v, factor out v to the rt. I think that's everything.
Yeah.
So, pretending my solution looks like this, its derivatives would look like this, and if it solves that, it means if I plug all these guys into that, it should be 0. So, plugging in, here's what's going to happen. My y double prime is that guy. Minus 2r1 times the y prime, which is that guy. Plus r1 squared times the y. That is equal to 0 by assumption. Now, if that actually works out, consequence? Well, first here, I can divide both sides by the exponential because that's never going to be 0. So I can ignore that. Now let's actually start to group, guys. We're going to have a v double prime. Now what? I'm going to have a 2r1v prime minus 2r1v prime. See that? So this guy here is going to kill this. I would have an r1 squared v
Minus 2r.
plus an r1 squared v
That's 2.
minus 2r1 squared v's.
All
This seems like a
v
lot.
double prime is only left.
That's what this reduces to. Oh, what does that mean? Well, that means v prime is a constant.
Oh, yeah.
What does that mean? Well, this means v is a constant times t plus another constant. Now what does that mean for y2? y2 is v times y1. Well, that means it's going to be ct plus d times e to the r1t. Now, this is going to be ct e to the r1t plus d e to the r1t. Now, this is already like the c2 to c1 e to the r1t. This is redundant, because when I plug it into the general solution, they're just going to be combined into the c1. So I can ignore So what is the second solution? T e to the r1t. It's always going to be t times e to the other guy. Not in general, for a second order linear differential equation with constant coefficients that has one root. The second guy is always going to be t times the first guy. Now, for other kinds of differential equations, the function t here could be something different, and we're going to look at specific ones where the t really becomes an ln of something or whatever. We're going to see that later. But in this situation, it's really nice. Everything really breaks down.
So for the part where you ignored it,
Yes?
I saw some questions where that one also is in the original solution, so you have to multiply t again, and then that.
No, you can always ignore this.
Okay.
Because if you plug it back into the general solution, if you assume that the general solution is c1y1 plus c2y2, what you're going to find is c1 times the e to the r1t plus c2 times all of this. It's going to be ct e to the r1t plus d e to the r1t. This is going to give us c1 e to the r1t plus c2 times ct e to the r1t plus c2 times d e to the r1t. Now this I can just combine, right? That's going to be c1 plus c2 times d, all that times r1t, which is just some other constant.
Yeah.
Relabel it c1. And then I'm going to be left over with the c2 times t to the r1. So this guy never really contributes anything. He gets absorbed into that guy, so you might as well just not worry about it.
A new question.
Yes?
If v double prime equals 0, so wouldn't it just be easier to assume that v prime would be 0?
No, because that's not true. Why would you assume that?
Because the derivative is 0.
Sure, but the derivative of 5 is also 0.
Yeah, it's just
The derivative of 7 is also 0. The derivative of pi is also 0. So if the derivative is, if something is 0, your integral is not 0. Not necessarily. Your integral is a constant. Now, that's reduction of order. It works. In this case, it was super easy. It's not always that easy. Why it's called reduction of order is that usually what happens is the guys that have the v's are going to cancel out at minimum. Whenever this works, that's how you're going to know it works. The v's are going to die at a minimum. So then you'll have guys with v double primes and v primes. Then you just do a substitution. U equals v prime, u equals v prime, and then you get a first order equation. You have a u prime and a u. And so you go from a second order to a first order, which is why it's called reduction of order. Now, sometimes you get lucky and it's super nice to the point where everyone gets canceled out except the highest derivative, which is in this case. And yeah, it's not always this nice though. In general, things can be a little bit more sketchy. But Yeah, that's why when I have a repeated root, I just know the second guy is going to be t times the first guy. It's just something I automatically know now because I've gone through this process. I didn't pick a particular differential equation. This works in general. That's reductive work. Now, probably the question that would have preceded this is, why would I look for another guy in the first place? Right? If I have a second order differential equation, I get one solution. Why am I not satisfied? Why is that not good enough?
Do you need a solution for every order?
You need a solution for every order. So one, there's an intuitive feel for why. Now, intuition is not a proof or anything, but it kind of tells you that there might be I'm missing something. One, if there's a second derivative and you want to get to the original, you would think I need to integrate twice. That makes sense. Integrating twice gives you two arbitrary constants. It's going to be very weird to have a double derivative and only have one arbitrary constant. So that's the first thing. It kind of doesn't make sense for there to only be one solution to a second order. Right? Because if I just have C1 e to the R1t, that's one guy. Where's the other arbitrary constant? At least I should have another constant being added. Right? But the thing is, it wouldn't make sense for a constant to be added because you'd realize that if you added a constant and you plug it into the differential equation, you'd get that constant equals 0. Right? So I know there's some other variable function out there. So that kind of leads us to think about some other things. So here are some facts. So ay double prime plus by prime plus cy equals 0 is a solid with constant coefficients. Now, assuming y1 is a solution, then if we assume that y1 is a solution, then it turns out that any constant times y1 is also a solution. That is going to be the first important point. What does this actually mean? If y1 is a solution, that means that if I were to plug y1 here, ay1 double prime plus by1 prime plus cy1, I would get 0. Now, if we substitute y equals a constant times y1, what's actually going to happen? Well, I'll have a times a constant times y1 double prime plus b times a constant times y1 prime plus c. This was a bad idea. Let's call it c1. C1. So c times c1, y1 is equal to 0. Now, what do you know about the derivative of a constant times a function? It's the constant times the derivative of the function. The constant factors out. So the constant is going to factor out from here as well. The c1 is going to factor out from here as well. So c1 literally factors out of everything unscathed. And what do you have left over? And guess what? That guy is 0 by assumption. So in other words, this is a solution. It doesn't even matter what the C1 is. So C1Y1 is a solution. That's a very important fact. Once someone finds a solution to a differential equation, a constant times that solution is automatically a solution, right? And don't just think, oh, maybe I can find the second solution by multiplying by a constant. Kind of redundant. It doesn't mean anything. So you might think, oh, maybe the next guy is a constant. It's not going to work if you plug it in. Maybe the next guy is a constant times this. Yeah, well, that's kind of automatic. It's not really fair to actually say that. Besides, the C1Y1 is going to be the general solution anyway. So, okay. So here's another thing. Suppose y1 and y2 are solutions. to the sole. Then, if I take C1 times Y1 plus C2 times Y2, this is called a linear combination of Y1 and Y2. Any of you are in 346? Yeah, linear combination. I'll define it later. Linear combination. We're going to talk about linear independence, linear combination, all that good stuff, which in 392 I don't think.
No, they'll do it.
Yeah. I don't know why they call it linear algebra. It's such a.
It's
a hoax.
It's a pretty ironic name.
It's just calculate. It's not even linear algebra.
Yeah, and it's like matrix algebra.
Yeah.
The prelude to linear algebra. Like this is what is in the preface of the
Linear
book
algebra.
on linear algebra. A linear combination of Y1 and Y2. So it turns out that that guy is also a solution. Now that also is not going to be hard to prove because derivatives are nice. If I plug that guy in for the y's, then what's going to happen? Well, the derivative of a sum is the sum of the derivatives. So I would have AC1 y1 prime plus AC2 y2 prime. And again, derivative sum is sum of derivatives, and I can actually factor the constants out. I don't have to write this equal to 0 yet. You're going to see that it has to be 0. It's not a choice. So this is equal to this. This is going to be equal to, now I group all the guys that have the y2s and the y1s separately. So if I group all the y1s, I would have C1 times AY1 double prime. And I have, here's another y1 plus C1 times a BY prime, Y1 prime. That's this. And then here I have plus C1 times C Y1 plus I have C2 times AY2 double prime. I would have C2 times B Y2 prime, and I would have C2 times C Y2. This of course gives us C1 times AY1 double prime plus BY1 prime plus CY1 plus C2 times AY2 double prime plus BY2 prime plus C2Y plus CY2. Now, what is that? Well, I assume that these are both solutions, which means these both will give us 0. And I end up the answer being 0.
Really?
Which means that's a solution. It makes the differential equations true. Now, the obvious question is there a third one? Can I add a C3Y3?
I'm sure you can.
Does it make sense? Yes, I can, but should I? Is the ultimate question. And it turns out that the answer is no. It turns out that once you find two solutions that are linearly independent, I'll talk about that, to a second order ODE, any other solution that you can conjure up will be a linear combination of the previous two. If I find a third guy, there's going to be a way to construct that third guy by taking a constant times the first one and a constant times the second one and adding them together. The third one is never going to be something new, something different. I'll always be able to construct them from a form like this. And so that's when we start to get into the existence and uniqueness. Now we're starting to think, okay, so if I have a second order, there are going to be two solutions, but no more. And I can kind of always expect for there to be two solutions to a second order. Now, why that is, we will get into next time. But the plot thickens.
Go to last week.
Huh?
Go to last week.
Huh?
Go to order.
A third order will have 3, a fourth order will have 4. I have quizzes to get done. No one keeps reminding me. Hold on.